I just discovered a project that measures the absolute slowest single instruction ever executed by a CPU, and the winner takes over a minute. We spend most of our lives optimizing code. We chase lower latency, higher throughput, and better cache locality. But the assembly hall of shame takes the exact opposite approach. It searches for the absolute floor of single instruction performance. That means finding the instruction that takes the longest to complete. This is not about emulated instructions or software traps. It is about real hardware executing real instructions. The repository is hosted by Zorixixix on GitHub. It currently holds nearly 700 stars. The goal is simple. Find the instruction that takes the most cycles to finish. The rules are strict. Only one instruction counts toward the score. You can do whatever setup you need before that instruction. But the timing starts the moment that specific opcode executes. All platforms must be in their factory stock configurations. No hardware mods, no overclocking, no underclocking. Just raw, unadulterated silicon doing what it does best when forced into a pathological scenario. So what is the current champion? It is the FXR Store 64 instruction on an AMD Ryzen 7 5800H processor. The score is just over 198 billion cycles. That translates to 62 seconds. That is more than a full minute for a single instruction. How do they achieve this? It involves the PCIe fabric. The FXR Store 64 instruction loads a 512-byte floating point unit state from memory. Usually this is fast, but here, they map that memory to a high-latency MMIO region in the PCIe fabric. Then they starve the fabric. They use a fleet of hammer cores to pound a different high-latency MMIO register with tight 4-byte reads. This saturates the PCIe root complex. CPU 0 must queue its data behind all that contending traffic. It is a brilliant demonstration of how hardware architecture can bottleneck a single instruction. There are also honorable mentions. One notable entry is an unaligned YMM0 load. This instruction is VMOV. It forces non-posted word transactions from stalled GPU registers. This specific setup was used to break the fundamental design of system management mode in a project called SMEI. It shows that even instructions we consider standard can become pathological when the underlying hardware is pushed into a weird state. The repository tracks these edge cases because they matter. When you are writing kernel code or virtualization layers, you need to know that an instruction can take forever under specific conditions. To understand how big the champion is, look at the bottom of the leaderboard. Number 27 is the standard NOP instruction. It does nothing. It takes one cycle. Number 26 is NOP 16. It uses the data 16 prefix to force a longer decode time. It takes 20 cycles. Number 25 is RDTSC. It reads the time stamp counter. This is often used for timing itself, so it has its own overhead. These entries establish the baseline. They show us that normal instructions are instantaneous compared to the champion. The gap between one cycle and 198 million cycles is staggering. The community discussion is fascinating. One commenter asked if 62 seconds for one instruction is possible without cheating. The answer is yes, but it depends on your definition. Another commenter pointed out that it is kind of cheating because the slowness is not the CPU. It is the memory controller and the PCIe bus. The CPU can map other device memory spaces into its own address space. They configure it to target the slowest device on the bus. It is not native in the sense that a push or pop instruction would use, but it is valid hardware behavior. You are using the machine as designed, just in a very contrived scenario. Why do we care about a 60-second instruction? Because edge cases exist in production. A commenter noted that this becomes important when you do something like coherency checks. If you are running a virtual machine, a split lock could allow the guest to do as the host. Linux detects VMs doing split locks by default. Ironically, one user reported that the detection itself slowed down their VM enough to cause a Windows guest blue screen. This proves that these pathological instructions are not just trivia. They affect stability and performance in real systems. The Assembly Hall of Shame documents these limits so we can avoid them or account for them. If you want to see the full leaderboard, you should check out the Assembly Hall of Shame repository. It is hosted by Zori Xixiks on GitHub. The link is in the description. You can see the code for each entry. You can see the assembly snippets. You can see the specific hardware used. It is a treasure trove for low-level enthusiasts. It reminds us that hardware is complex. Even a single instruction can take a lifetime if the conditions are right. Thanks for watching. If you enjoyed this deep dive, subscribe for more tools and open-source projects. See you next time. Check the link in the description to explore the Assembly Hall of Shame yourself. If you want more deep dives into low-level tools, hit that subscribe button. I will see you in the next one.